This is an integral that less than 2/3 of all chipmunks can answer, and that's a real statistic. So we want to evaluate the integral from 1 to 2 of 1 over x times the square root of x squared minus 1. Wow, what an interesting question. Let's have a look at how we can do this. First of all, let's just notice that this is kind of an improper integral because when you plug the number 1 into this thing, you end up doing 1 divided by 1 times the square root of 0. But of course, the square root of 0 is 0, and so we're dividing by 0. Bit cheeky. We'll come back to that later. So it is an improper integral. We're going to need to do some limit business. Don't worry about it just yet. Let's focus for the moment on the indefinite version of it. So that means at the moment, maybe I'm going to do this in a different color. I'm only going to focus on the integral, the indefinite integral, which means that there's no limits, of x times the square root of x squared minus 1. Okay, so we're going to come back with the limits later, but let's just do this guy first, and then we'll do the limit stuff. Okay, cool. So what are we going to do? Well, we're going to do a substitution, and the substitution is not particularly obvious, but guys, this is a trig substitution, and the giveaway for why we're going to do a trig substitution is we've got the square root of either 1 minus something squared or something squared minus 1. A lot of the time, that's going to involve a trig substitution. Now, if we had the square root of 1 minus x squared rather than x squared minus 1, I'd be tempted to do a substitution involving sine or cos. However, sine squared minus 1 and cos squared minus 1 are not really great here. They're not good at all. So we want to use a different trig function. Now, it's difficult to exactly explain why your mind should go to this if you don't recognize this. But what I will say is there is a trigonometric identity that says that 1 plus tan squared of, let's say, just a for now, is identical to sec squared of a. Okay, if we do a teensy bit of rearranging, we can see that tan squared a is then identical to sec squared a minus 1. So what we have is if x was like sec theta or sec u or something, then we'd end up getting the square root of tan squared in the denominator, and that's going to play really nice. Not just because it ends up being tan, but it's because of the nature of the substitution. When you do that substitution, you're going to get a nice value for dx over du or d theta, whatever. Let me show you what I mean, okay? So what we're going to do is we're going to let x equal sec theta. So I know it seems a little bit random, like, okay, sec, that's a bit strange, but you guys will see how it all comes into place. So first of all, let's find what dx d theta is. So the derivative of sec is sec times tan. Okay, so the derivative of sec theta is sec theta times tan theta. Okay, then let's rewrite the integral with that substitution in mind. So we've got 1 over x is sec theta, so sec theta times the square root of, this is going to be sec squared theta minus 1 there, all inside the square root. And dx, guys, we can see that we can replace that with sec theta times tan theta d theta. And guys, this is the glorious part. Everything cancels out, right? So sec and sec, they cancel out. And as I said, guys, sec squared theta minus 1, just by using that identity, that is tan squared theta. And we're doing the square root of it. So what we really have is the integral of tan theta, because this is the tan theta that's here, divided by another tan theta. And of course, that's just the number 1. So what we end up with is just the integral of the number 1 with respect to theta, which of course is just theta plus c. Now, what is theta? Remember, we said that x was sec theta. So theta is inverse sec or arc sec of x. Of x. Sorry, I'm getting them all muddled up, but yeah, of x. So what I'm saying is that our integral, all in all, the integral of 1 over x times the square root of x squared minus 1 dx is equal to arc sec of x plus c, of course. Now, you might say, I don't like arc sec. I don't like the idea of that at all. That's absolutely fine. So what we're going to do is we're going to replace arc sec with something a bit nicer, because arc sec is not really one of the kind of official ones. It's not one of the big players, right? So I mean, obviously sec is 1 over cos, so maybe we can express this in terms of arc cos in some way, which would be a lot nicer for us to visualize. So let's just quickly do that. So what I'm saying here, I'm going to do this in a different color as well, is I've got this function, I'm going to call it y, and it is arc sec x, and I don't like that. So I want to come up with another expression for this. So what I'm going to do is I'm going to rearrange this and see if I can do that. So I'm going to take sec of both sides. So sec y would be sec of arc sec x, which by definition, that's just going to be x. And then sec y, remember guys, that's the same thing as 1 over cos y. So 1 over cos y is x. Bit of rearranging, we can see then that cos y would have to be 1 over x. And then finally, to get y on its own again, we can take inverse cos. So y is also inverse cos of 1 over x, or arc cos of 1 over x. So what I've said is that y, which is arc sec x, is the same thing as arc cos of 1 over x, or cos to the minus 1, they're the same thing, whatever you prefer. So this is a much nicer way of visualizing this. So what we've really said is our integral, which is arc sec x, is also arc cos of 1 over x, which is maybe a little bit nicer. So we've just worked out that this thing is equal to arc cos of 1 over x plus c, which is a lot nicer than, again, arc sec x, in my opinion. Okay, now that we've done all the heavy lifting there, we can then just evaluate it because it's actually the integral from 1 to 2. So now we're coming back to this. So this is equal to, and again, we have to treat it as an improper integral because when x is 1, we're dividing by 0. So it's an improper integral. So we need to rewrite this as the limit as, let's say, t approaches 1 of what this evaluates to, which we now know is arc cos of 1 over x. So we've got arc cos of 1 over x evaluated from t to 2. Okay, 2 is fine. 2 doesn't cause any problems, but 1 does. So we have to take the limit like this. And this is easy stuff now, guys, because this is just the limit as t approaches 1 of, this is arc cos of 1 over 2, plugging 2 in that is, minus arc cos of 1 over t, like that. Now, this is then the limit as t approaches 1 of, well, what is arc cos of a half? Well, arc cos of a half is pi over 3 because cos of pi over 3 is a half. Okay, so pi over 3 that is, minus, again, we've got arc cos of 1 over t. Now, let's actually let t be the number 1 here and see what happens. So this ends up being pi over 3 minus, and then we've got arc cos of the number 1, right? Because it's 1 over 1. And arc cos of the number 1 is just 0, right? Because cos of 0 is 1. So this is just 0 here. So we've got pi over 3 as our final answer. So the answer to this question, that again, less than 2/3 of all chipmunks can answer, by the way, if that wasn't immediately obvious, because chipmunks are not capable of doing a definite integral. But nonetheless, less than 2/3 of them can answer it. I'm trying to say this with a straight face. But the answer is pi over 3. So that's the answer. That's the value of this integral. And in our journey, we did a little bit of trig. We did a bit of trig substitution. We did a little bit of deriving some cool little identities here, like arc sec is the same thing as arc cos 1 over x. We did a little bit of limits, kind of, and we ended up getting a nice number in terms of pi over 3. But that's a fun one. I think that's a fun one. And yeah, it's a kind of integral that Simon and Alvin can do, but Theodore can't, if you guys know Alvin and the Chipmunks. Anyway, guys, I'm just giving you some maths brain rot at the end of that video. Thank you so much for watching, and I'll see you in the next one. Cheers.